Hi, my name is Tyler Hamans. I'm a fourth year physics student here at the University of Georgia's Department of Physics and Astronomy, and I'm here with my fellow fourth year physics student, Kristen Rollins. And today we are very excited to show you our final project in Physics 3330, which is using silver nanorods for surface spectroscopy for microplastic detection. And you wonder why our department is always out of money. We will go over the experimental proposal and how we chose and designed our experiment and what went into that. We will also get into a bit of background about me and Chris and why this experiment is important to us. I will then let Chris take over and explain the experimental setup and how the experiment was performed. But if you were hoping I would shut my mouth and go away, I am sorry to say, but I will be back to explain the different instruments in the videos, as well as to explain the results of the experiment and the conclusions we made from it. So sorry about that. So for our experimental proposal, as stated earlier, we decided to do spectroscopy for microplastic detection, and we did this because of several reasons. The main reason is because this topic is not actually that well researched, and the effects of microplastics on humans are not actually that well understood. And this is just mainly because of how difficult it is to actually do good experiments on microplastics. So we wanted to develop something that would potentially make that process easier. In our original proposal, we actually were thinking about doing this with Raman spectroscopy, but based on the recommendations of our professors, we decided to switch over to localized surface plasma resonance because it's just easier to work with. The second main reason is because this project happens to be in an area where both me and Chris's interests overlap. I've always been interested in astronomy, and one of the biggest fields in astronomy today is astronomical spectroscopy, and where we get to see the chemical makeups of things like planets, stars, asteroids, things of that nature. And for Chris, he's always been interested in the application of advanced physics to things like medical science. So, how can we make medical science better through physics? So, this just happened to be at an area where both of us had a good idea of what we wanted to do, and both of our interests matched on this one. As stated earlier, this technology does offer several major advantages over traditional chemical testing. One of which is it's just simply cheaper to do because you don't have to dispose of everything when you're done with it. And even if you had the displeasure of having a COVID test done before, you would know that when you're done with doing the COVID test, you have to throw the whole thing out. But with spectroscopy, you don't have to do this, so you could potentially do much more testing and have much more up-to-date results because you wouldn't have to worry about incurring cost for it. And the second main reason is because it's actually a form of non-destructive testing. And what non-destructive testing means is that you do not destroy your sample in the process of testing. So some chemical tests, when you do their testing, it destroys the sample because you just can't put it back in its original form. You ruin whatever data you got from it. So if you wanted to do a different test on it, you just couldn't. So for spectroscopy, this is a big advantage because you can, if you wanted to do a different test that maybe a spectrometer can't do for whatever reason, then you can do that and you wouldn't have to make that decision of whether you wanted to do this test or the other test. And I will hand this off to Chris so he can now explain the experimental setup and how this procedure went.
So for the experimental setup, we used a plasma cleaner to help clean and decontaminate the silver nanorod substrates. We used glass dishes and magnetic stir to mix and contain the solutions we use for the silicon coating and for further cleaning of the silver nanorod. We used the UV-2450 spectrophotometer and UV probe for taking the measurements we needed and for analyzing them as well. And as for the chemicals we used, experiment, we used deionized water. We needed that to clean the dishes before and after the use, and for cleaning the aging substrate of this excess solution. We had ethanol, ammonium hydroxide, and tetraethyloxanine for our silicon coating solution, which is to help ensure the lasting of the silver nanorods so that it didn't decay before we could complete our experiment, and for the protection of it as well. Now for the experimental procedures. So first we had to clean all of our dishes and glassware with deionized water before we used anything. That way it could all be nice and clean and no foreign materials were in it. So afterwards, we made sure to air dry it, and we did so just because we didn't want any paper towel residue inside the dishes. So we did it. So we let it dry and we let it sit until they're completely dry. And we had to use a pipette to remove some of the excess water initially, and then let this happen. So once that happened, we set up the magnetic stirrer and put it underneath the hood on a hot plate, and then we added the solution consisting of 30 milliliters of ethanol and 4 milliliters of deionized water into this dish, and set the stirrer to 600 RPM. While that was going, we used the plasmon cleaner to thoroughly clean and sanitize the silver nanorod before we put the silicone coating on it. So to do so, you first put the silver nanorod in, and then you reduce the pressure in the chamber using the vacuum, and then add the gas needed into the chamber until it reaches the specified pressure. It was 7 torr for 90 seconds for us, and then we set it for 600 mTOR and let it go. After that, we put on the tuner to make sure we can actually get plasma. And once we did that, we now had plasma. We let it run for about 90 seconds and then shut off. It was completely clean after that. And we turned on the gas, let pressure come back to normal. And then now, after that was done, we could use this over nanorod. So now we added 500 milliliters of, I'm going to call it TES for simplicity. So we added 500 milliliters of TES to a solution of ethanol and deionized water, and then added the silver nanorod into that solution and let it run for additional 20 minutes. After that, we added 560 milliliters of ammonium hydroxide to the solution, and that was helped us complete the silica coating, and we let that run for 5 more minutes. After that, we drained the solution, we rinsed it with deionized water, just to make sure everything's clean, that it was nice and coated, and again, we let this dry, we let it air dry once again, and after that we came back the next day, it was time for us to use and calibrate the spectrophotometer. So for calibration, so to calibrate the spectrophotometer is actually quite simple. So using UV probe, once you turn it on and actually get it to run, it might take 1 or 2 tries to make it actually get fully on and running. Once that happened, we use the perfect white to make sure that we had something that was at least theoretically close to 100% reflectance. That way it could know exactly what maximum reflectance is, so it could be perfectly calibrated. So now, once we have that, we establish a baseline, which so it knows, okay, this is what everything is being referenced to in terms of reflectance, and now it's calibrated. So after that, we use measurements. So when we did it, we first had a test substrate just to make sure we could have it positioned right in the spectrophotometer, and so that the light hit it correctly. And then we could also measure how much angle we could turn on each thing. So once I use the test, when I put it onto the slit that goes into the spectrophotometer, and we kind of at dashes measured it from 0 to 180 in 15-degree increments, so that we could get a good reference point and good amount of data for each angle from 0 to 180. So now we did that. Now it was labeled. We tested it. So I tested by putting this test one in and measuring the reflectance multiple times just to confirm that it was exactly how it was supposed to be. And once I did that, then we started the actual experiment. So now for each subsequent substrate, going from the lowest length to the highest length, we put the substrate into the spectrophotometer starting at 90 degrees. Then we went from 90 to 0, and then we went from 90 up to 180 on each of them. We did that for every single AGNR substrate. And once we did it for all 5 substrates, we had all of our data, and then now it's time for us to analyze and graph our experimental results.
Okay, going over our experimental results, we did come to a few findings. Um, each of these graphs represents a different thickness, or basically what the diameter of the rod. So at 400 nanometers, we didn't really get much activity at all. Everything seemed pretty uniform. But at 800 nanometers, we did get a spike at 90 degrees between 250 and 800 nanometers in wavelength. And at 1200 nanometers, we actually got one that was at 0 degrees, but it was from 400 to 800 nanometers, which was actually very interesting because it was pretty much an exact opposite. And at 1600 nanometers, we actually got several different spikes at different angles. One was at 0 degrees, and one was at 105 degrees, and one was at 90 degrees. And each of these kind of started around 450 nanometers all the way to 800 nanometers, which was very interesting. Um, 2000 didn't really give us much results. It was pretty uniform throughout the entire thing. So now we can take a look at the S&P polarization by taking the average wavelengths at each angle. And we see on each of these graphs, with the S polarization being represented by 90 degrees and the P polarization being represented by 0 degrees. And we're looking for how the reflection changed based on the rod thickness and the wavelength between the two polarization angles. We do actually expect to see a change regardless of whether there are microplastics present or not, but we are looking for major changes in our dips, our rises in reflection. The most obvious one you can see between S and P is 800 nanometers rod thickness, and the other one that's kind of less obvious but still pretty well defined is at 1600 meters, and this is where we saw the multiple peaks from earlier. So plotting this data on a polar graph allows us to see the change in intensity at different angles much easier. And as you can see, there's still a pretty obvious bump at 800 nanometers for the rod length, and that's at 90 and 270 degrees. But the interesting part is that if you go to 1600 nanometers for the rod thickness, you can actually see a sort of shift between 90 and 105 degrees and 255 degrees to 270 degrees. And this is probably due to the fact that there were multiple wavelength spikes at the point in the it's not as well defined as 800, but it is still pretty easy to see. One of the interesting things, though, is that one of the things you can't actually really see on the original graphs, but you can see here, is that there is a spike around 400 nanometers. It is very small, and we originally thought this might just be an artifact of data, but based on the fact that you can also see a small spike at 105 degrees at one of the earlier graphs, makes us believe that this is actual real data and not just an experimental artifact. You can also see that most of the wavelengths also kind of spike around 0/180 degrees, except for 800 and 2000 nanometers. So based on these results and the previous data, the most likely candidate for what type of plastics these probably are is either polystyrene or PVC based on the nanorod thickness and the refractive index. We also concluded that these are probably the most likely areas to look for microplastics just due to the amount of data we actually got at these two areas. Um, so for future experiments, we actually do plan to use more data more accurately around these areas. So we're probably going to do things at the 1400 to 1800 nanometer range more often. So while this experiment did yield valuable data on microplastic research, it also taught us how we can conduct experiments that aren't pre-planned and how we can improve on our experiments in the future. We hope that we can actually continue this research because we do think this actually does actually have pretty good applications for the future, and we hope that this technology can one day be in kind of like every doctor's office and how we can use that to help people because it would be very nice if everyone could just get like their COVID test back almost immediately and not have to worry about costs or anything. But we do have a lot of work beforehand before that happens. But to be honest, I'm not in this major because it's easy. So, but if you would like to ask us a question, you can feel free to contact us at one of the emails below, and we will try to get back to you in a timely manner. But most of all, we just greatly appreciate your attention, and we thank you for letting us present our project to you. We know that it was probably very long, but we hope it was enjoyable.